Alright, I'm back for part 2, which is time zone 2, HL paper 2. I hate HL stuff. As you saw, well, if you've been watching, the paper 1 just had a lot of, I don't know, unnecessary, tedious, kind of obscure algebraic manipulation, which is generally why I'm not a fan of them. But whatever. Yeah. For the sake of time, just like last time, I'm skipping the SL questions. So here it is, time zone 2, paper 2, and then question 1, SL, go watch the video. Question 2, SL, go watch the video. Question 3, SL, go watch the video. Question 4, also SL. And question 5, damn, okay. So here's our first actual HL question. So let me just copy this over. Oh yeah, I forgot to take care of that noise. Okay, we have a continuous random variable x. Here's the probability density function between 0 and 1. And then we need to show this is the expected value. And then this is the variance. Okay, easy enough. Pull out your formula booklet. And then just go to the statistics. And then right here in the HL section, here is how you do the expected value of a continuous variable. So we're just going to do the same thing. So this is just going to be the integral from 0 to 1 of x times our probability density function. Like that. Okay, so the n plus 1 is just the coefficient, so we can pull that out of the integral. And then x times x to the power of n basically just means you have x to the power of n plus 1 from this x. And this is an easy integral to do. Oh, I should write the dx. This is going to be a little messy. It's all going to be all over the place. So n plus 1, take the integral of this. This is going to be 1 over n plus... Shoot, how does this work? 1 over n plus 2. N plus 2 from 1 to 0. Geez, almost forgot my basic integration for a second. Okay, so then we have n plus 1, 1 over n plus 2. Oh, this is kind of, okay. If you're just gonna plug in 1, then 1 goes here, minus 0. Whatever, here it is. Anyways, yeah, plug in 1 for x, so your first term is just going to be the 1 over n plus 2, plug in 0, second term 0, multiply this in, there you go, easy. Next, show that this is the variance. So again, you have formulas for your variance, especially, well, there's two. You can either do this integral, which kind of sucks, or you can do this one, which is related to the expected value, which you found out in part A. So we're gonna use that one. So what does this say? The variance of x is going to be the expected value of x squared minus the square of the expected value. So we already know what this is from part A, and then we just need to do this. And so we're just going to do this integral again, but it's going to be for x squared. So the only thing that changes for this integral, well, there's a couple of things that change. First off is, I believe this is x squared, which means that this is going to become x plus to the power of n plus 2. And then we just go through the integral again. And if you're just following all of these steps, the only thing that changes is this going to be, what, n plus 3? Yeah, the only thing that really changes is that instead of n plus 2 from the n plus 1, we now have n plus 3 from the n plus 2. Okay, so that means that my variance is going to be n plus 1, n plus 3, I think it was a minus, n plus 1 over n plus 2 squared. Okay, and then if we keep simplifying it, it'll look like this. So, this needs a common denominator so that these can add together. So the first term I'm going to multiply by n plus 2 squared, and then this one I'm going to multiply by n plus 3. So now they have a common denominator of n plus 2 squared times n plus 3. We have over here n plus 2 squared times n plus 1, and then minus n plus 1 squared times n plus 3. And I think we need to show that this becomes n plus 1. Sure, okay. Does it? It might. Okay, I'm gonna factor out the n plus 1. So then I'll have n plus 2 squared minus n plus 1 times n plus 3. Okay, and then ideally, I think if you expand this out, this should be 1, because this is what I wanted to show here. Okay, so let's just do that real quick. This is n squared plus 4n plus 4, and then we're going to subtract n squared plus 4n plus 3. Yeah, so as you can see, the n squared, the 4n, subtract from these ones, or vice versa, and then 4 minus 3 is 1. Okay, so done. Next question. This looks like a combinatorics one. Okay, 8 runners. Andrea and Jack are 2 of the people. Find the total possible number of ways that these runners can finish if Jack finishes immediately after Andrea. Okay, so there's 8 people. So let's say, what's the easiest way to do this? I'm just gonna, okay, don't get confused. You're HL students, but we have 8 runners. So we have Andrea, we have Jack, and then we have the 3rd runner, the 4th runner, the 5th, the 6th, the 7th, and then the 8th. Okay, so find the total number of possible ways that Jack can finish if he's immediately after Andrea. So what we do is we basically package them together, making sure that Jack finishes after. So we consider these guys one item. And so what you're really doing is you're arranging 1 2, 3, 4, 5, 6, 7 groups. And the way that they're arranged right here, Jack is after Andrea, so this is just 7 factorial. So 7 blah 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 times 3 times 2 times 1. Again, you're arranging 7 things. These people plus the group. So these 6 people plus the group. And then it says that Jack is always after Andrea, so this is a pretty typical question where you want to group things together, except normally they might ask you, like, Jack and Andrea have to be like together. And then if that's the case, like, it doesn't work with like running, but like, let's say you're putting books on a shelf, or like these are 8 people that need to sit on a bench. If Andrea and Jack need to sit together, then you need to take this and then times it by 2, because there's like 2 arrangements of Andrea and Jack. In this specific one, Jack is always after Andrea, but in a different question, Jack could have come before her and they're still together. So you'd have to multiply this by 2, the arrangements of their group. But nevertheless, that's not the thing, so whatever. And then we need to find the possible ways that 8 runners can finish if Jack finishes any position after Andrea. Okay. So if you just think about it, Jack just needs to come after Andrea, and it doesn't matter where he is. So there are a total of 8 different ways to arrange this, and obviously if you think about it, half of them have Jack come first, and then half of them have Andrea come first. There's no other way that you can arrange it unless you think about it like that. So if we want to just find out all the ways that Jack finishes after Andrea, then we just take half of the total amount of arrangements. And for the sake of time, I'm just going to leave it like this, and we're going to move on. Okay, consider this complex number, sure. Show that the real part of this is 0. Okay, so we have a complex number. It's made from a division of 2 complex numbers. So what I'm going to do is I'm just going to simplify this. So as you know from how to divide by complex numbers, or at least hopefully you know, we're going to multiply this by the conjugate to make sure that our denominator is not going to be complex. So then we'll have 1 plus z squared over 1 minus z squared, because now this is a difference of squares. At least I think that's how it works. And then then we need to consider z as this, and I'm going to shorten this to CIS. Should I? No, I don't think so. Okay, never mind. Okay, and then now I make a substitution. So the numerator is actually, why don't I just expand this out first? 1 plus 2z plus z squared over 1 minus z squared. Okay, now I make a substitution. My numerator, 2 cosine theta plus 2 sine 2i sine theta plus cos theta plus I sine theta squared over 1 minus cos theta plus I sine theta squared. Okay, so this is just 2 times z, and then I just multiply the 2 in. Okay. Then we should expand these squareds. So what is that? That's cosine 2 theta plus 2i sine theta cosine theta, And then what? Minus sine squared theta? Yeah, because this is going to make the minus, and then sine squared is sine squared. Okay, and then likewise, down here, we'll have that. And then does it tell me what I'm supposed to do? Oh, show that the real part is this. 0. Okay. Okay, I'm gonna rewrite this. So there's that. And then there's this. And then all of this is divided by, geez, okay, let me draw a reasonably straight line. Okay, so if I distribute the minus in, then this becomes a minus and this one becomes a plus. I think I'm gonna mess this up. Ah, shoot. Oh well, I just wasted a bunch of time. Okay, sorry, I should have, like, I have the right idea, but I should have made the substitution first, because the conjugate depends on the actual complex number. Jeez. Okay, sorry. Boop. Okay, substituting this in, the denominator, here's the real part of the complex number in the denominator, so I should have multiplied by this conjugate instead. 1 minus cosine plus I sine. Geez. So then I'll have 1 minus cosine here plus I sine here, and then okay, geez, okay, I'll leave a comment to make sure that you skip to the actual proper part. Okay, so down below I'll have 1 minus cosine squared plus sine squared theta. So this will make a difference of squares like that when you multiply the conjugates, and then over here, if I multiply this out, okay, I'll just write it out. Okay, so yeah, so multiplying the numerators out, you should get this. So this times that, and then this times this, and then that times that, and then this times that. Okay, and then there we go. No more complex numbers. Jeez, okay. So we're going to simplify a bunch of things. So first off, this is a difference of another squares. So this is going to become 1 minus cosine squared theta. Notice that this plus cosine I sine is going to cancel out with this minus cosine I sine when we collect like terms. So those are going to cancel. So we'll have plus 2I sine theta, and those come from the ones, the two ones that I have, multiplied by I sine theta. And then I have minus sine squared theta, and then stuff. Okay. And then I'm supposed to show the real part is 0. Okay. So you need to show that. Let me rearrange this, because this is the only complex part of our number, the thing with the I. Okay, and then as you can see, I need to show that this is 0, and then that's pretty easily done because you have a cosine squared and a sine squared. We can just use the Pythagorean identity. Either way you want to use it. I'm going to change the 1 into sine squared plus cosine squared. And then as you can see, this will cancel out with the minus sign, and this will cancel out with that cosine. So you're only left with a complex number, or not a complex number. You're only left with a complex number with an imaginary component. So you have 2 sine theta over the stuff times I, and then basically this means that the real part is 0. You don't have a real part. It's all imaginary. This is the only term which has an I in it. Okay, moving on. Oh nice, we're in the long stuff. Oh no, not yet. Wait, no, not yet. This one's an 8 mark. That's not quite long enough. Okay, write down the first 3 terms of this binomial expansion. It's to the negative exponent, so we're going to, with ascending powers of t, 3 terms. We're going to use the extended binomial theorem in HL, which is right here. I'm just going to copy it. Okay, hopefully I don't get copyright infringement for this music. But I feel like video game music is relatively safe. Okay, so this is 1, and then this is t, and then this is -1. Okay, so that's 1, so that's easy enough. We don't have to deal with that part, because that's all going to be 1. So 1 plus t to the power of -1 is equal to 1 plus -1 times b times t plus -1 times -2 divided by 2 factorial, which is just 2 times t squared. And then again, all of these are just 1 because a is 1. So simplifying this, I have 1 minus t plus t squared. I think this is, yeah, this is just one. Positive one. Nice. Oh, that's only worth 1 mark. Okay. By using the Maclaurin series for cosine and the result of part A, show that the Maclaurin series for secant up to and including the term in x4 is this. Okay. So we need the Maclaurin series for cosine, and again, that's in your formula booklet right here. So I'm going to copy this. And I'm supposed to find the Maclaurin series for secant, right? Up to x to the power 4. Okay, so you need to relate it to cosine. It's the inverse, or not the inverse, the reciprocal of cosine. And then we have the Maclaurin series of cosine, which is this. And then 4 factorial is 4 times 3 times 2, which is, what, 24? Dot, dot, dot. Right? Yeah. Okay, and then I need to show it looks like this. And I need to use part A. Ah, here, okay. So you gotta remember that -1 is the reciprocal, and I just said that this is literally the reciprocal. So what am I doing here? Or, yeah, okay. So this is equal to 1 minus x squared over 2 plus x to the power of 4, 24, dot, 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 to the -1. Now notice that this only has 2 terms, and that's because when you expand this out, how do I explain this? Here. So if this is, we want this up to x4, but that doesn't mean that we include the x4 here. Basically, if this is my A, right, and then this is my T, when I just use the first 2 terms and then I ignore this term, notice that you get a t squared. So I'm going to square this x squared, so this x squared makes an x to the power of 4. So I'm not going to include this part of the Maclaurin series so that I can use the expansion properly here. Okay. So that means that this is going to become 1 minus t plus t squared. And then how do I get 5 over 24 from this? Did I mess something up? Okay. Well, we'll just keep going for now. I think this is a plus. And then we're going to square t squared. So I have x to the power of 4 over 4. But that's not what I want, because they already tell me what it should be. So I messed up this part. Okay, you know what I'm gonna do? Check the mark scheme, which is right here. Oh, I'm done. Okay. You know what? Forget what I said. We do need to include this term. It's just the whole thing is gonna be t. Okay, hold on. Let me just do this real quick. X squared minus 2 plus... Okay, yeah, that was dumb of me. I shouldn't have omitted that. So basically, this whole entire thing is going to be my plus t. Yeah, okay. I'll add another timestamp. So yeah, take this, actually, yeah, inverse reciprocal Maclaurin series, make that the reciprocal so that we can use part A, and then this whole thing is going to be t. So you have 1 minus negative x squared over 2 plus x to the power of 4 over 24 dot 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 dot, and then plus negative x squared over 2 plus x to the power of 4 over 24 plus dot 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 squared. Yeah, okay. Okay, yeah. I jumped ahead of the gun. So this is going to be 1 plus x squared over 2 minus x over 4 over 24. And then technically there is more, but then these are higher powers of x. So x5 and more. And then over here, when we square this, so basically there's just, this is going to multiply by another one of itself. And if you remember, we're only considering this up until x to the power 4, and there's only one term when you multiply these two together that is x to the power 4 or less. And that's when you multiply these two together. Because if you multiply this one with this one, it makes x to the power 6 and higher, and vice versa. If you multiply this one or higher terms in with the first term, it also makes x to the power 6 or higher. So we're only multiplying these first two terms. And that's going to make positive x to the power 4 over 4. And then plus dot 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 1 plus x squared over 2. And then if I want to make this one term, I'm going to make this 24 by multiplying this by 6 on the top and the bottom. And then if I'm subtracting 1, there we go. This is how you get your 5. Okay, sorry about that. That was dumb of me. But this is what I was talking about here, about the mistake I did about forgetting the rest, because when you multiply it, there's only going to be one term. So it happens here. Okay. Next up. Using Maclaurin series for arctan and then our result from part B, this one, show that this limit, find this limit. Okay. Sure, whatever. Let's just do this. So we need to find the limit as x goes to, is it infinity or 0? To 0 of x times arctan, is it 2x or just x? 2x. Don't make it easy for you. Divided by secant x minus 1. Okay, so this is going to be x times the Maclaurin series of arctan, which again is in your formula booklet. Right there. So my x is going to be, well, 2x in the question, so I'll have 2x plus 2x to the power 3 over 3. This is a minus. Okay. Minus dot dot dot. And then I just found out the secant Maclaurin series right here. And this is minus 1. And then my calculus teacher always harped on me for always making sure the limit is with every part of every side of the equal sign you use. Okay, this looks straightforward. So this one will cancel out with that one. This x multiplies in. So you're going to get the limit as x goes to 0 of x squared over 2 plus the rest of this. And then we'll have 2 x squared minus did I do this right? Okay, multiply this out, 8 x to the power of 4 over 3 dot 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 dot. Okay, for the sake of that. Okay, and then if we want to evaluate the limit, notice we do have like an issue with a bunch of zeros everywhere. So what we're going to do is we're going to factor out an x squared from the numerator and the denominator. Because then what you're left with is this. And then now these x's can cancel, and then when you evaluate the limit, all of these terms which still have x's in them are going to become 0 and go away. So your limit is going to be 2 divided by 1/2, which is 4. Okay. That's a nice question. And then now we're on to section B. This one's an SL question, so go watch that video. This one is not an SL question because it has volume of rotated whatevers. Okay. So here's a function, and then we're gonna rotate it from the x-axis to this one, 360 solid revolution. Okay. Oh, here's a graph of it right here. So it goes from here to this line. This line is ln 16. I call it ln, natural log 16. Anyways, whatever. And then we need to show that this is the cubic units. Is this a paper 2? This is a paper 2, right? I haven't used a single calculator yet. Like calculator function. That's weird. Well, the SL questions, I've probably had to have used it, but none of these HL ones I have. Oh well, okay. Sorry. Volume is, what is it? Pi from 0 to the natural log of 16 of the function squared. Yeah, you can just check your formula book. This is the formula for the volume of a solid of rotation, or rotation of solid, or whatever it's called. Okay, and then they do want you to show this in, well, it has K in it, right? So we can't even use a calculator for this. So let's see. I'm gonna square the actual function itself, because then I'll have in the numerator k squared times e to the power of x, and then down below I'm not going to actually expand it because we can make a u substitution, since the derivative of 1 plus e to the x is e to the x. So if you want to, you can make a u substitution. Because here's your ex dx that turns into the du. Either way, as an HL student, you can also probably just eyeball this integral. So we have our k squared, we have our pi, and then this is going to be the integral of, I think it's just 1 plus e to the x to the negative 1 from natural log 16 to 0, or 0 to natural log 16. Yeah. I think there's a negative here. Right? Negative 1, bring it down, take away 1, you get the squared, chain rule, you get e to the x, which goes here. Yeah, here you go. So here's the integral, and then we're going to use fundamental theorem of calculus. So you got 1 plus e to the natural log 16 to negative 1 minus 1 plus e to the 0 to negative 1. Okay. So this is 16, which means that this is 17, which means that this is 1 over 17. And then this is 2, which is 1 over 2. We're going to subtract these. So this is 2 over 34. And then this is 17 over 34. So this is negative 15 over 34. And then if we multiply that by negative k squared times pi, you get your answer. The k squared, the 15, the pi, and the over 34. Right? E to the power natural log 16 is just 16. 16 plus 1 is 17. Take the reciprocal, 1 over 17. This is 1, that's 2. Reciprocal is 1 over 2. It's a little bit of fraction math. So that whole big bracket right here is negative 15 over 34 multiplied by this. You get that. Okay, easy. Okay, next Pedro wants to make a bowl with this volume. Okay, find the value of k. Sure. So this is equal to 300, which means that k is going to be 34 times 300 divided by 15 pi square rooted. Our first calculator usage, at least from HL stuff. So 34 times 300 divided by 15 divided by pi. Okay, and then square rooted. So 14.7. Okay, and then I didn't copy the rest of the question. Okay, find OA. What's OA? OA is right here. Okay, since this is just from the x-axis to your function, isn't OA just when you plug in the x value 0 into your function? Yeah, it is. Okay. So if I plug in 0 into here, then I'll get k e to the power 0, so that's just 1, divided by 1 plus e to the power 0, which is just 1, so this is 1, so k over 2. Okay, so OA is 14.7 divided by 2, so I'm going to just take this number divided by 2, 7.36. Or whatever. And then find BC. Same thing, right? Yeah. So BC is right here. This is your x value. So I need to find out f when you put in natural log 16. Okay. So then I'll have k. E to the natural log 16 over 2 over 1 plus e to the natural log 16. Okay, so dividing by 2 is the same as multiplying by 1/2. So I'm going to just use a little bit of log rules to bring it inside, so that I'll have natural log 16 to the power 1/2, which is natural log 4, which means that I have k times e to the natural log 4, which is just 4, so this is 4k, and then divide by 17, because this part's going to be 16, so 1 plus 16 is 17. 4k over 17. So 4 times 14.7 divided by 17. So let me go back. So here's my k times 4 divided by 17. 346. Okay. For design purposes, Pedro investigates how cross-sectional radius of the bowl changes. By sketching a graph of the derivative of f, find where the radius of the bowl is decreasing most rapidly. Decreasing. Okay, whatever. We're gonna graph the derivative. Okay, so what was my function? K e x over 2, 1 plus ex. So take the derivative of this, which is the quotient rule. So k divided by 2 e to the x over 2 times 1 plus e to the x minus k e to the x over 2 times e to the x divided by 1 plus e to the x squared. Okay, this is just quotient rule. So put this in our GDC. And whatever, it's ugly, but the calculator can handle it. Oh shoot, but k was 14.7. So so 14.7. Oh, I should put, this is gonna take a lot of brackets, isn't it? (14.7) divided by 2 times e to the power of x divided by 2 bracket, another bracket, 1 plus e to the x bracket minus bracket k 14.7 times e to the x divided by 2 bracket bracket e to the power of x bracket, oops, not there, delete, bracket bracket divided by 1 plus e to the x to the power of 2. Okay. And then my window is from 0 to the natural log of 16. Graph it. Okay, and then we want to find out where it's decreasing the most. So this is the derivative, so these are the values that it is decreasing by, and where it happens the most is the minimum value. So I'm going to calculate the minimum. So left bound, right bound, make a guess. So 1.76. Okay, so boop, boop, boop. what is that? Negative 1.83, negative 1.84. Okay, so here's my graph. So find out where it is decreasing the most rapidly, here. And then state the cross-sectional radius of the bowl at this point. So now I'm just going to take this x value and then plug it into the actual function, because again, the value of the function is the radius of the bowl at that point. So now I plug in 1.76 into the original function here. That's annoying. Okay. So what's k? 14.7 times e to the power of x, which is 1.76, divided by 2. And then this is going to be divided by 1 plus e to the power of x, 1.76. Okay, 5.2. There you go. And then is there more? Nope. Last question. Okay, and we're still slightly under an hour. But then this one's 21 marks. Oh my god. I thought I could... Well, I did screw up twice, so that's like a... That slowed me down by like 15 minutes or so. Okay, let's see. Here's a function, arcsine, sure. Show that f is an even function. Easy enough. So an even function means that the negative x is the same, the function at negative x is the same as the function at x. And, well, you can show it that pretty easily, because this is going to be arcsine negative x squared minus 1 over negative x squared plus 1. And then if you're going to square it, it's going to end up, oops. If you're going to square the negative x, it's going to become positive x anyways. Positive x squared. So this is equal to f of x, so even. Easy. Now, by considering the limits, show that the graph has a horizontal asymptote and state its equation. Okay, a horizontal asymptote is the limit as x goes to basically positive or negative infinity. And we're going to do what we did in the other question, and I'm going to factor out an x squared. Because then this just basically means that as we take the limit as x goes to infinity, anything that still has a division by x, so this and this cancel out, they become 0, they approach 0. So this becomes the arcsine of 1, which is just 90 degrees pi over 2. Oh, sorry, there. Okay, so we have a horizontal asymptote here. Next up, show this is the derivative. What am I taking the derivative of this thing? Okay. Okay, it's a composition of functions, so I'm going to take the chain rule. The first thing is the derivative of arcsine, which is in your formula book probably. Here. So 1 over the square root of 1 minus x squared. So 1 over the square root of 1 minus x squared, which is the second function, the inner function, this thing. And then we're going to multiply that by the derivative of the inner function, which is a quotient rule again. So that's 2x times x squared plus 1 minus x squared minus 1 times 2x over x squared plus 1 squared. Okay. Now it does tell us what we want. If we want it to look like this. So first let's check out my numerator. This 2x times 1 is going to cancel. No, it won't cancel. Whatever. Okay, let me just expand this out real quick. 2x cubed. Okay, never mind. No. Okay, this x squared is going to cancel with this minus x squared. But then this minus makes this a plus. So then we're going to have 2 of these things. You get 4x in the numerator. Okay. Sorry, I'm just trying to do this quickly. You can just multiply these in and multiply this in and collect like terms. You'll get 4x. And then we'll probably need to clean this up down here. And we will notice that there's only one term in our square root, so I'm going to write the 1 with a common denominator of the second term. Like that. Oops. So we'll have x squared plus 1 squared minus x squared minus 1 squared over x squared plus 1 squared here. And then we had a 4x here and an x squared plus 1 here. X squared plus 1 squared. Okay, my square root should only be x squared, so I'm gonna need to simplify this further. Oh yeah, okay. So my numerator is going to be x to the power of 4 plus 2x squared plus 1 minus x to the power of 4 minus 2x squared plus 1. Okay, and then this cancels out with that, and then this one cancels out with that one, which leaves me with 4x squared. Okay, I think I see where this is going. Okay. So here's the x squared that we need in our square root. Okay. So this is 1 over 2. Square root of 4 is 2. Square root of x squared. And then this is x squared plus 1. This needed an x. Okay, for some reason, yeah. And then this, the square root and then the square will cancel out. And the reason why we don't cancel it out here is because we don't necessarily know whether the original x is positive or negative. So you have to leave it like this. For example, if x is negative 3, if you square it, you get 9. And then if you square root it, you get 3, which is, they're not the same, right? But you know that x squared plus 1 is always positive, which is why you can just cancel out the 2. And then this is gonna be rewritten like that, because this is just the reciprocal of a fraction, which means that you literally just take the reciprocal of the fraction. And then we're done, right? Yeah, we are. So this divides with this. This gives us our 2x. And then this cancels out with one of those. And we have shown what we needed to show. Okay, done. Then by using this expression and this result here, show that f is decreasing for x is less than 0. Okay, so this means that we have 2x, and this is f prime, by the way, x squared plus 1, and then, okay, for x being negative, then 2 times x is going to be negative. X, the absolute value of x is always positive, and like I said earlier, x squared plus 1 is positive, so that means you essentially have a negative number divided by a positive number. So your derivative is always negative, i.e. F is decreasing. That was easy. How much was that worth? 9 marks. Is this not enough to show that? Or is that 9 marks between the two? Oh, it's between part A and B. Or part I and II. Okay. Okay, we have a function g. Okay, it's the same thing, but this one's only defined for this. Find expression for g inverse. Okay. So g is arcsine, and then it was all that stuff from before. Okay, so we can call this y, and then this basically means that well, we'll just go through the algebraic process. We switch x and y, so this becomes x. We have arcsine. Don't write it like this on your exam. I'm just being lazy, trying to save time. Okay, and then we solve for y, so take the sine. This means that sine of x is this stuff. Multiply the denominator over. This is a pretty standard finding the inverse. Distribute this in. And then collect your y terms to one side. So I'm gonna move these around a little. I should write that better, just to avoid confusion, because the y squared is not part of the sign. Okay, common factor out the y squared, divide it over. Okay, and then take the square root. So this is plus or minus the square root of 1 plus sine x over 1 minus sine x. Now this is a relation, it's not a function, and they want us to have it as a function, right? Yeah. Find expression for a function. Okay. So we need to choose whether or not it's going to be positive or negative, the y's. Oh, and then that's why they told us this. So this is our domain right here, right? Domain of f, which means that the range of f is going to be positive numbers, because the domain of, sorry, the range of f, this isn't even f. Hold on, okay. This is the domain of G, which means that the domain of G inverse, no, the range of G inverse is this y is greater than or equal to 0, otherwise it's positive. So wait, do you have to justify my answer? No, geez, okay. Okay, so this means G inverse of x is the positive y's. Since domain of G is this, that means that the range of G inverse is this. So we are choosing the positive ones. So here's your justification. And then, is there more? Am I on the last one? No, state the domain. Okay. The domain of G is basically the range. The domain of G inverse is the range of G, and then the range of this is the range of arcsine, right? The range of arcsine is from negative pi over 2 to pi over 2 inclusive. Okay, so that means that the domain is the same thing. Negative pi over 2 to pi over 2. Okay, I want to get this done soon. We're still under an hour and a half. Sketch the graph, clearly indicating asymptotes with their equations, stating the values of any axes or intercepts. Okay, that's easy enough. We're just gonna GDC it. GDC. Okay, home stretch. Make sure I'm in radian mode. Okay. So we have 1 plus sine x bracket bracket divided by, oops, this should be a minus here. One minus sine x bracket 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 square rooted to the power of 0.5. And then my domain is 0 or more. Oh, 0. No, my range. The domain of my inverse is negative pi over 2 to pi over 2. So negative pi over 2 to pi over 2. And then my range is going to be 0 and up. So I'm just going to have it at -1. And I don't know what it's going to be. I'm going to just say 5. Graph. Okay, indicating any asymptotes and any axes intercepts. So we have this one. And then we have an asymptote, right? Where was the asymptote? Oh yeah, okay. So from part B, G has a horizontal asymptote at G has a horizontal asymptote at pi over 2. So then that means that the inverse has a vertical asymptote at pi over 2. And you can sort of see that right here, pi over 2. Okay. Pi over 2. Indicate your intercepts. So calculate the value of your function at x equals 0, which is 1. Okay, that's easy. 1. And then your graph will go woo. Okay, not quite like that. Woo. Nice. And then we're done, right? And thus we reach the end of the exam. Obviously I omitted like half of it because it was SL stuff. But, alright, time to check my mark scheme and see how we did. And then I'll end it off. And then I'll guess I'll do a paper 3, probably tomorrow. Okay, this one, show this, show that. So I showed it, don't need to check the answer key. Oh, I guess you need to use a calculator for this. I just skipped that part. Question 7. Okay, 7 factorial ways. Oh, you can just leave it like that. Oh, and you can also just leave it like that. Okay, guess you really didn't need a lot of calculator work. Okay, so that one's done. This one is a show. So again, I've shown that, so that's fine. This one, write down the first 3 terms. I think I checked the answer key for this though. So that's correct. Part B, show that this is the Maclaurin series for a secant. So I showed that. And then using the result from part B, find the limit as x goes to 0. Did I find the limit? Yeah, the limit is 4. The limit is 4. Okay, so that's good. Okay, and then we skip down to question 11. So, oh yeah, first question is showing that this is true, which we did. The volume's 300, so what does that mean K is? K is 14.7, yep. Okay, that means that OA is 7.36 and BC is 3.46. Yep. Okay, sketch the graph. Here it is, 1.76. Okay. And then that means, yeah, X is this. Find the radius, 5.2. Okay, that's done. Okay, show that this is even. Show that it's even. Find the horizontal asymptote. So pi over 2. Pi over 2. Okay, show this. I showed it. Explain why it's decreasing. Well, I kind of explained it here. So there you go. Find an expression for G inverse. So G inverse is this thing. Here. Okay. State the domain. Here's my domain. Yep. Oh, whoops. I messed this up. You're not supposed to include pi over 2. My bad. Don't include pi over 2. Don't include pi over 2. Because, right, it's a vertical asymptote there. My bad. My bad. And then sketch the graph. Here's the graph. Are we, oh, right, we're supposed to include this. There was an x-intercept here. My bad. Oh well. Okay, overall, I'm done. Much easier time with this one than the paper 1. And this didn't even have a lot of calculator work, so all of these questions could have been almost a paper 1. A lot of these could have been a paper 1. Except for obviously sketching a graph. Sketching the graph. Doing these calculations. But overall, yeah, I think this paper 2 was easier. Okay, thanks for watching, you guys. And yeah, see you later for paper 3.